Imagine waking up one night and noticing that one star in the sky is suddenly brighter than all the others combined. Not the sun, not the moon. A distant star that now burns like a second daylight. What you're seeing is not beauty. It's a warning. Somewhere in our cosmic neighbourhood, a massive star has just died. In a fraction of a second, that star collapses under its own gravity, then explodes with more energy than our sun will produce in its entire lifetime. A supernova. One of the most violent events in the universe. Powerful enough to rip atoms apart, flood space with deadly radiation, and send shockwaves travelling at millions of kilometres per hour. Now here's the terrifying question. What if that explosion happened inside our own solar system? What if the shockwave reached Earth? What if the radiation stripped away our atmosphere? What if life on this planet suddenly faced extinction without any way to escape? Tonight, we're going to travel through this cosmic disaster step by step. From the first flash of light in the sky, to the invisible radiation storm that follows, to the long-term changes that could permanently reshape Earth, Mars, and the entire solar system. This isn't science fiction. Scientists already know what supernova radiation does to planets, and the results are far more dangerous than most people imagine. If you love deep space mysteries, cosmic catastrophes, and real science explained in cinematic detail, make sure to subscribe and turn on notifications, because this channel explores the most extreme events the universe can create. Now, let's place a supernova inside our solar system and see what really happens. The moment the supernova detonates, the first thing that reaches the solar system is not fire, not shockwaves, not debris. It is light. A sudden, overwhelming flash of radiation that races outward at the maximum speed the universe allows. If the exploding star is close enough, this flash would become brighter than the full moon, brighter than any object in the night sky except the sun itself. For several seconds or minutes, depending on distance, Earth would experience what looks like a second sunrise happening in the wrong part of the sky. At first, most people would not understand what they are seeing. Astronomers would immediately recognize the signature, an intense spike in gamma rays, X-rays, and visible light detected by satellites and ground-based observatories. Emergency alerts would begin spreading through scientific networks almost instantly. A nearby star has just collapsed and exploded. A supernova has occurred inside our cosmic neighbourhood. Within minutes, the invisible danger arrives. Gamma radiation from the explosion begins striking Earth's upper atmosphere. This radiation does not burn cities or create firestorms on the ground. Instead, it interacts with atmospheric molecules, breaking apart nitrogen and oxygen. This triggers chemical reactions that start destroying ozone molecules at an alarming rate. The ozone layer, Earth's natural shield against harmful ultraviolet radiation, begins thinning rapidly. At the same time, high-energy particles called cosmic rays start flooding into the solar system. These particles travel at near-light speed and can penetrate spacecraft, satellites, and even parts of Earth's atmosphere. Space agencies would detect massive radiation spikes. Astronauts aboard space stations would be ordered to move into shielded modules immediately. Satellites not designed for extreme radiation exposure would begin malfunctioning or shutting down entirely. communication systems would experience disruption. GPS signals could degrade. Some satellites might permanently fail due to radiation damage to sensitive electronics. Power grids on Earth could experience surges as charged particles interact with Earth's magnetic field, similar to powerful solar storms but on a much larger scale. In space, the effects are even more dramatic. The solar system's outer regions would be the first to encounter the expanding shockwave of energized particles. While the physical shockwave itself moves slower than light and will take years to arrive, the radiation front immediately bathes planets, moons, and spacecraft in intense energy. The magnetospheres of Jupiter and Saturn would flare violently as they attempt to deflect incoming radiation. Auroras on these planets would intensify beyond anything previously recorded. Closer to the Sun, Earth's magnetic field begins working at maximum capacity. It deflects many incoming charged particles, but not all of them. Some penetrate deep into the atmosphere. Airline flights at high altitude, especially near the poles, would be forced to reroute due to radiation exposure risks. Aviation authorities would ground many long-distance flights temporarily. On Earth's surface, people would not immediately feel physical effects. The danger is invisible and delayed. However, scientific instruments would already show something deeply troubling. Atmospheric chemistry is changing rapidly. Nitrogen oxides produced by radiation begin accumulating. These compounds accelerate ozone destruction. Within days, ultraviolet radiation reaching Earth's surface would start increasing. This increase in UV radiation does not cause instant catastrophe, but it begins stressing ecosystems. Plants become more vulnerable to damage. Phytoplankton in the oceans, which form the base of the marine food chain, start experiencing reduced productivity. These microscopic organisms are extremely sensitive to ultraviolet exposure. A decline in phytoplankton activity begins disrupting oxygen production and carbon absorption on a planetary scale. Meanwhile, radiation exposure continues affecting technology. Space telescopes may shut down. Communication satellites experience errors. Some military and weather satellites fail completely. Emergency systems struggle to adapt to the sudden loss of orbital infrastructure. Astronomers calculate the distance of the supernova and begin modelling worst-case scenarios. If the explosion occurred within about 50 light-years, Earth faces serious long-term consequences. If it occurred within 10 light-years, the situation becomes far more severe. The closer the explosion, the more intense the radiation and particle bombardment. In the hours following the explosion, Earth's skies begin changing subtly. The atmosphere glows faintly in unusual colours as charged particles interact with air molecules. Night skies become brighter due to enhanced auroral activity even at low latitudes. People in regions that never normally see auroras may witness shimmering curtains of light stretching across the horizon. Inside scientific control centres, panic mixes with urgency. Teams analyse incoming data. Governments activate emergency coordination groups. The problem is not evacuation. There is nowhere to escape. The threat is planetary in scale. As radiation continues interacting with Earth's upper atmosphere, temperature patterns begin shifting. Not dramatically yet, but enough to register on climate monitoring systems. Atmospheric circulation becomes unstable as chemical composition changes. Some regions experience unusual weather anomalies within days. The Sun itself is not immune to the effects. While the supernova radiation does not physically damage the Sun, it alters the charged particle environment throughout the heliosphere. The solar wind interacts with incoming cosmic rays, creating turbulence across interplanetary space. Spacecraft travelling between planets experience navigation disturbances and radiation spikes. Mars, with its thin atmosphere and weak magnetic field, suffers even more severe exposure. Radiation penetrates deeply into its surface layers. Any future human habitats on Mars would face dangerous radiation levels. Robotic systems may experience failures. Scientific instruments detect massive atmospheric loss acceleration. Back on Earth, governments begin issuing public health warnings. People are advised to limit sun exposure due to rising ultraviolet levels. Protective measures such as UV shielding, specialized clothing, and controlled outdoor activity become recommended. Schools and workplaces adjust schedules. In coastal regions, marine scientists observe declining plankton populations within weeks. Fish migration patterns change as food availability shifts. Coral reefs begin showing stress due to increased radiation and temperature instability. Agriculture also begins facing challenges. Some crops show reduced growth rates. Farmers notice abnormal leaf damage in sensitive plant species. Greenhouses become increasingly important for food security. Despite all of this, the planet does not collapse immediately. Life continues. Cities remain standing. Oceans do not boil. But the foundation of Earth's environmental stability has been weakened. In space, the expanding debris cloud from the supernova continues moving outward. Over the coming years, it will gradually enter the outer solar system. When it finally arrives, it will compress the heliosphere, the protective bubble created by the Sun's solar wind. This compression allows even more cosmic radiation to enter the inner solar system. This is only the beginning. The first phase of a nearby supernova is not destruction. It is exposure, radiation, atmospheric damage, technological disruption, biological stress. It quietly undermines planetary systems that evolved under stable cosmic conditions. Human civilization now stands at the edge of a slow-moving cosmic disaster. One that does not explode cities overnight, but steadily pushes Earth into an environment it was never designed to handle. And as scientists continue monitoring the incoming radiation storm, one terrifying realization becomes clear. The most dangerous part of the supernova has not even arrived yet, because the shockwave is still traveling, and when it finally reaches the solar system, everything changes again. As days turn into weeks after the supernova's initial flash, the solar system enters a new phase of danger. The radiation storm does not simply fade away. Instead, it continues to bombard planets with high-energy particles, steadily altering space itself around the Sun. Scientists begin noticing something alarming. The heliosphere, the invisible bubble created by the solar wind that shields the solar system from much of the galaxy's radiation, is shrinking. Normally, this protective bubble stretches far beyond Pluto, deflecting many cosmic rays. But the pressure from the supernova's expanding particle cloud begins compressing it inward. The boundary of the heliosphere moves closer to the Sun. As it shrinks, more interstellar radiation is able to penetrate deeper into the solar system. This change is subtle at first, detectable only by deep space probes, but its consequences are enormous. Earth, Mars, and the inner planets become increasingly exposed to radiation that would normally be blocked. Space becomes more hostile. The region humans once considered relatively safe for exploration turns into a radiation minefield. Satellites begin failing at higher rates. Solar panels degrade faster. Sensitive electronics suffer permanent damage. Space agencies scramble to adjust spacecraft operations, switching systems into radiation-hardened modes and shutting down non-essential instruments. Some satellites are lost entirely. Astronauts aboard orbital stations face difficult decisions. Radiation exposure limits are reached much faster than normal. Emergency shielding protocols become permanent procedures. Extended space missions are cancelled. Plans for lunar or Martian exploration are suspended indefinitely. On Earth, the atmospheric effects continue compounding. Ozone depletion worsens as nitrogen oxides persist in the stratosphere. Ultraviolet radiation reaching the surface increases further. Skin cancer risks rise sharply. Crops experience stress. Some plant species show visible leaf damage patterns similar to radiation burns. Forests begin showing subtle changes. Certain tree species become more vulnerable to disease as UV radiation weakens natural defense mechanisms. Insects that rely on visual navigation patterns tied to sunlight and polarization signals become disoriented. Entire ecological chains begin shifting behavior. The oceans suffer quietly but severely. Phytoplankton populations decline further. These microscopic organisms are responsible for producing a large percentage of Earth's oxygen. Even a small reduction in their activity has global consequences. Carbon absorption decreases, accelerating greenhouse effects. Oxygen production slows slightly but steadily. Fish populations begin migrating unpredictably as food chains destabilize. Coral reefs, already sensitive to environmental stress, experience bleaching events at unprecedented scales. Marine biodiversity declines across multiple regions. Weather patterns grow more erratic. Jet streams shift. Storm tracks change position. Some regions experience prolonged droughts while others face repeated flooding. Climate models struggle to predict behavior accurately because the atmospheric chemistry has entered unfamiliar territory. Governments around the world implement new emergency policies. Infrastructure protection becomes a priority. Power grids receive additional shielding upgrades to protect against geomagnetic disturbances triggered by cosmic radiation. Hospitals prepare for increased cancer treatment demands and radiation-related illnesses. Public awareness grows. News outlets broadcast updates about radiation levels and space weather alerts. Panic does not dominate yet, but anxiety spreads. People begin realizing that this is not a temporary space event. It is a long-term planetary crisis. Meanwhile, astronomers continue tracking the physical debris from the supernova. The expanding shell of energized matter travels outward at thousands of kilometers per second. Although it will take years to physically reach the inner solar system, its approach creates increasing turbulence in interstellar space. When the leading edge of this shockwave finally begins interacting with the outer solar system, the effect becomes measurable. The Kuiper Belt region experiences unusual particle densities. Instruments aboard deep space probes detect dramatic changes in plasma flow. As the shock wave compresses the heliosphere further, the Sun's magnetic field struggles to maintain stability. Solar activity becomes more chaotic. Sunspots increase unpredictably. Solar flares occur more frequently as magnetic field lines interact with incoming interstellar particles. This creates a dangerous feedback loop. Solar storms combined with supernova radiation amplify space weather effects around Earth. Geomagnetic storms intensify. Power outages become more frequent in vulnerable regions. Satellites experience cascading failures. Mars suffers even more severely. With its thin atmosphere and weak magnetic field, the planet becomes exposed almost directly to cosmic radiation. Atmospheric loss accelerates. Any future colonization plans become nearly impossible without massive shielding infrastructure. Venus and Mercury also experience atmospheric and surface radiation effects, though Venus's thick atmosphere provides some protection. However, increased solar and cosmic radiation further destabilizes already extreme planetary environments. Back on Earth, life adapts slowly. Some organisms begin evolving radiation resistance traits. Certain bacteria and extremophile species thrive in higher radiation environments. These changes take generations, but early signs appear in laboratory studies and natural ecosystems. Humans rely increasingly on technology to survive outdoor exposure. UV-resistant materials become standard for clothing and construction. Cities install protective coatings on windows and building surfaces. Agricultural systems move indoors using controlled environment farming. The global economy shifts dramatically. Space industries suffer major losses due to satellite damage and halted missions. Insurance markets collapse for orbital infrastructure. Governments invest heavily in radiation shielding technology and climate stabilization projects. Despite the growing crisis, Earth remains habitable. Life continues functioning, but under stress. Civilization adapts rather than collapses. However, scientists warn that the worst phase is approaching. The physical shockwave from the supernova is not just radiation. It carries massive clouds of ionized gas, dust, and magnetic turbulence. When this material finally reaches the heliosphere boundary, it will create a dramatic compression event. This compression could push the heliosphere so close to Earth's orbit that the planet temporarily loses much of its cosmic shielding. During this period, radiation levels could spike far beyond current safety thresholds. Models predict that during peak interaction, radiation exposure on Earth's surface could double or triple compared to normal background levels. This would severely impact ecosystems, human health, and technological infrastructure. Emergency planning shifts toward long-term survival strategies. Governments consider underground shelters for vulnerable populations. Hospitals prepare radiation treatment centers, raising the probability of collisions with Earth. Space agencies begin monitoring near-Earth objects more aggressively. Planetary defense systems are activated at high alert levels. Even small objects become dangerous when combined with weakened atmospheric shielding. Humanity now faces a layered disaster: radiation damage, climate instability, technological disruption, potential impact threats, and long-term ecological consequences that will unfold over centuries. The supernova is no longer just a distant cosmic explosion. It has become an active force reshaping the environment of the solar system itself, and as the shockwave continues advancing closer to Earth's orbital neighborhood, scientists realize that the next phase will not be measured in subtle changes. It will be measured in planetary transformation. Because when the densest part of the supernova cloud finally collides with the Sun's protective bubble, the solar system will enter the most dangerous period in its history. When the densest portion of the supernova's expanding cloud finally reaches the boundary of the heliosphere, the solar system enters a phase scientists describe as extreme compression. This is the moment when the Sun's protective influence is pushed inward harder than it has been in billions of years. The invisible shield that normally guards Earth and the inner planets from galactic radiation shrinks dramatically. In some models, it collapses to a fraction of its original size, leaving large regions of the solar system directly exposed to interstellar space. As this happens, radiation levels around Earth spike sharply. Cosmic rays flood into near-Earth space in numbers far beyond anything recorded in modern history. Satellites orbiting the planet begin failing in rapid succession. Even hardened military and research spacecraft struggle to survive the particle bombardment. Navigation systems degrade. Weather satellites lose accuracy. Communication networks become unstable. On Earth's surface, the effects finally become impossible to ignore. Radiation penetrating the weakened magnetic shield increases exposure levels at high altitudes and polar regions first. Pilots, airline crews, and passengers face dangerous radiation doses. Commercial air travel is suspended on many routes. Research stations in Antarctica and northern latitudes evacuate non-essential personnel. Hospitals begin seeing an increase in radiation-related symptoms among people who work outdoors, aviation personnel, and populations living at high elevations. Governments issue emergency advisories limiting outdoor activity during peak radiation periods. Protective shelters become standard infrastructure in many cities. The ozone layer continues deteriorating. Ultraviolet radiation reaches the surface in higher concentrations, damaging crops and ecosystems. Agricultural production declines in sensitive regions. Some crops fail entirely without protective coverings. Indoor farming expands rapidly, becoming critical for food security. Forests begin showing large-scale stress patterns. Leaves become thinner. Growth rates slow. Some tree species experience widespread dieback. These changes alter habitats for countless animal species. Migration patterns shift again as animals search for safer environments. In the oceans, the situation becomes even more concerning. With reduced phytoplankton activity and increased surface radiation, marine food chains weaken. Fish populations decline in some regions. Reports emerge of unusual die-offs among surface-dwelling organisms. Oxygen production continues decreasing at a slow but steady pace. Meanwhile, Earth's climate system begins responding to atmospheric chemistry changes. Increased nitrogen oxides and altered greenhouse gas concentrations disrupt temperature regulation. Some regions experience intense heat waves, while others face unexpected cooling. Seasonal patterns become unpredictable. Storm systems grow stronger and more chaotic. Hurricanes intensify due to warmer surface waters combined with unstable atmospheric circulation. Lightning activity increases. Extreme weather events become more frequent. The Sun itself reacts to the heliosphere compression. Solar magnetic activity becomes increasingly unstable. Solar flares erupt more frequently. Coronal mass ejections strike Earth's magnetosphere repeatedly. stacking on top of the already elevated radiation environment. Each geomagnetic storm further disrupts power grids and communication systems. Blackouts become more common in vulnerable regions. Governments rush to upgrade infrastructure with better shielding, but the pace of disruption outstrips preparation. Space becomes nearly inaccessible. Launch windows close. Astronaut missions are cancelled indefinitely. The idea of routine space travel disappears. Humanity is temporarily trapped on Earth, forced to adapt to a changing cosmic environment. As months turn into years, scientists begin noticing deeper biological consequences. Increased mutation rates appear in some organisms exposed to higher radiation levels. While many mutations are harmful, a few provide resistance advantages. Certain bacteria, fungi, and extremophile species begin thriving in high radiation environments. These changes ripple upward through ecosystems. New microbial communities form. Soil chemistry changes. Plant-microbe relationships shift. Ecosystems slowly reorganize themselves around new environmental pressures. Human society undergoes structural transformation. Governments centralize disaster response efforts. Emergency food programs expand. New international agreements form to coordinate radiation protection, climate adaptation, and planetary defense strategies. Economic systems strain under constant infrastructure repair costs. Insurance markets collapse in radiation-affected sectors. Investment shifts heavily toward underground construction, radiation-resistant materials, and closed-environment agriculture. Cities begin changing shape. More buildings are constructed partially underground. Transit systems expand subterranean networks. Shopping centres, schools, and hospitals move deeper below the surface to reduce radiation exposure. Despite all this, civilization does not collapse outright. Humanity adapts. But the psychological impact is profound. For the first time in modern history, people are forced to confront the reality that Earth is not isolated from cosmic disasters. The sky is no longer a distant backdrop. It has become an active threat. Public culture changes. Media coverage focuses on space weather updates alongside traditional forecasts. People check radiation indexes the same way they once checked air quality. Protective clothing becomes part of daily life in many regions. Children grow up learning about supernova radiation safety in schools. Generations adapt to this new normal, shaped by cosmic forces beyond human control. At the same time, planetary scientists observe another disturbing effect. As the heliosphere remains compressed, interstellar dust and particles begin penetrating deeper into the solar system. This material interacts with Earth's upper atmosphere, contributing to further chemical instability. Comet trajectories begin showing subtle shifts. Objects from the outer solar system experience gravitational disturbances caused by the shockwave's interaction with the Sun's magnetic environment. The probability of long-period comets entering the inner solar system increases. Planetary defense agencies escalate monitoring efforts. Radar systems track near-Earth objects continuously. Emergency deflection technologies are placed on high alert. Humanity prepares for the possibility of impact events triggered indirectly by the supernova. Mars remains exposed, suffering extreme radiation damage. Robotic missions cease functioning. Any remaining infrastructure deteriorates rapidly. The planet becomes even more hostile than before, reinforcing Earth's role as humanity's last major refuge. Venus and Mercury experience intensified solar interactions. Their already extreme environments become even more unstable. While these changes do not directly threaten Earth, they demonstrate how deeply the supernova's influence reaches across the entire solar system. As the years pass, the initial shock of the supernova transforms into a long-term planetary crisis. Humanity realizes that this is not an event with a clear ending. The radiation environment may take thousands of years to return to normal levels. Adaptation becomes the only path forward. Scientists develop improved atmospheric protection technologies. Artificial ozone restoration systems are deployed in targeted regions. High-altitude drones release chemical compounds designed to slow ozone loss and stabilize atmospheric chemistry. Massive solar shield concepts are proposed to block incoming radiation during peak exposure periods. While expensive and technologically complex, prototypes begin orbiting Earth, offering localized protection. Global cooperation strengthens out of necessity. Space agencies, environmental organizations, and governments coordinate like never before. Survival becomes a shared project rather than a national competition. Yet even with all these efforts, one truth becomes impossible to ignore. The supernova has permanently changed the solar system's environment. The Earth that existed before the explosion is gone. What remains is a planet struggling to stabilize itself in a harsher cosmic neighborhood. And while humanity fights to preserve its home, scientists continue tracking the fading shockwave, knowing that its influence will linger for generations. Because the real danger of a nearby supernova is not just destruction, it is transformation, a slow, relentless reshaping of the conditions that allowed civilization to exist in the first place. And now, Earth must either adapt to this new cosmic reality, or face the possibility that its era of stability has finally come to an end. As the supernova's influence settles into the long-term structure of the solar system, Earth enters what scientists call the chronic exposure phase. This is no longer a sudden disaster event. It is a sustained environmental shift that reshapes life, technology, and planetary systems over decades and centuries. Radiation levels stabilize at a new elevated baseline. They do not remain as extreme as during the peak compression of the heliosphere, but they never fully return to pre-supernova conditions. The solar system's protective bubble slowly re-expands, yet it remains thinner and weaker than before. Interstellar cosmic rays continue penetrating deeper into planetary space, creating a permanent increase in background radiation. On Earth, this new radiation environment quietly alters biology. Mutation rates across many species rise slightly but consistently. Most mutations are harmful or neutral, but over generations they accelerate evolutionary pressure. Organisms that can tolerate higher radiation levels gain survival advantages. Certain plant species develop thicker leaf structures to block ultraviolet exposure. Some insects evolve darker pigmentation to absorb and dissipate radiation more effectively. Microorganisms that repair DNA damage efficiently begin dominating soil and water ecosystems. In humans, medical researchers observe subtle changes in long-term health patterns. Cancer rates increase despite protective measures. Reproductive biology shows minor shifts as DNA repair mechanisms are placed under greater stress. Governments invest heavily in genetic medicine, radiation therapies, and preventative healthcare programs to reduce long-term population impact. Urban environments transform even further. Architecture evolves around radiation resistance. Buildings use layered composite materials that absorb and scatter incoming particles. Windows incorporate ultraviolet filtering technologies. Public transit systems expand underground. Entire neighborhoods move partially below the surface, creating hybrid cities that exist both above and beneath Earth. Agriculture undergoes a revolution. Open-field farming becomes increasingly risky in many regions. Farmers rely more on enclosed environments, climate-controlled domes, vertical farms, and subterranean crop facilities. Artificial lighting replaces sunlight in many production zones. While food production continues, it becomes more energy-intensive and technologically dependent. Rural landscapes change. Some farmland is abandoned due to soil degradation and radiation exposure. Other regions adapt with specialized crop varieties bred for resilience. Genetic engineering accelerates as scientists create plants capable of surviving higher UV radiation and fluctuating climate conditions. The oceans continue absorbing the consequences. Marine life gradually adapts to the new radiation baseline. Some plankton species decline permanently, while others evolve radiation tolerance traits. Food chains reorganize. Fisheries shift locations as species migrate toward deeper or more protected waters. Coral reef ecosystems, already fragile, struggle the most. Many reefs collapse completely, replaced by simpler marine ecosystems dominated by hardy organisms. Ocean biodiversity decreases in complexity, but life persists in altered forms. Earth's climate system settles into a new unstable equilibrium. Without the original atmospheric chemistry balance, weather patterns remain erratic. Long-term climate models show increased variability rather than consistent warming or cooling. Some decades bring intense heat, others bring abnormal cooling events. Storm systems become more unpredictable. Regions once considered temperate now experience extreme weather cycles. Flooding and drought alternate rapidly. Infrastructure planning becomes more complex as historical climate data loses reliability. Human migration increases. Populations move away from high radiation zones and unstable climates. New megacities form in regions offering relatively stable environmental conditions. These population shifts create political and social tensions, forcing governments to coordinate relocation strategies. Meanwhile, technological development accelerates under pressure. Energy production expands dramatically. Fusion reactors become standard to power underground cities, climate control systems, and agricultural facilities. Renewable energy infrastructure grows in protected zones. Space-based solar collectors supplement planetary power demands. Artificial intelligence systems become central to planetary management. These systems coordinate climate stabilization, radiation monitoring, disaster response, and resource distribution. Humanity increasingly relies on predictive modeling to stay ahead of environmental changes. The psychological impact on society deepens. People grow up in a world where cosmic threats are part of daily life. The sky is no longer seen as peaceful. Space weather alerts become as common as storm warnings. Education systems emphasize planetary vulnerability and survival science. Cultural identity changes. The idea of Earth as an isolated, protected world fades. Humanity begins seeing itself as part of a larger cosmic environment, Influenced by events far beyond its control, space exploration remains limited during this period. Radiation conditions make long-duration missions dangerous. Plans for Mars and deep space colonization are delayed. Humanity focuses inward, stabilizing Earth before expanding outward again. However, scientists continue monitoring the fading supernova remnant. And technological intervention. Human society adapts structurally. Long-term planning replaces short-term development. Infrastructure is designed for resilience rather than convenience. Buildings are constructed with modular components that can be upgraded as conditions change. Political systems shift toward global cooperation. The supernova crisis demonstrates that planetary threats cannot be handled by individual nations. International climate and radiation management organizations gain unprecedented authority. Despite cooperation, inequality remains a challenge. Regions with access to advanced technology adapt faster. Less developed areas struggle. Global aid programs expand, but resource distribution remains complex. As centuries pass, Earth slowly stabilizes into its post-supernova state. The planet does not return to its old balance. Instead, it finds a new one, harsher, more unpredictable, but survivable. Humanity survives, not unchanged, not untouched, but transformed. Children born generations after the supernova grow up in a world shaped by cosmic disaster. They accept underground cities, artificial agriculture, and radiation protection as normal parts of life. They do not remember a time before the sky became dangerous. For them, this is simply Earth. Yet historians preserve records of the pre-supernova era. Museums display data showing how stable the planet once was. Educational programs teach how the explosion reshaped the solar system and forced civilization to evolve. This knowledge becomes a warning and a lesson, a reminder that Earth's safety was never guaranteed, that life exists at the mercy of cosmic events, and that survival requires adaptability, cooperation, and long-term thinking. As humanity enters this new era, scientists continue looking outward once again. With radiation levels slowly declining and technology advancing, plans for space expansion return to discussion. The supernova that once trapped humanity on Earth now becomes a catalyst for future preparation, because the next cosmic disaster is not a matter of if, it is a matter of when, and this time humanity intends to be ready. The solar system has been scarred by the explosion of a distant star, but it has not been destroyed. Instead, it has been reshaped into a harsher cosmic neighborhood, one where survival is possible, but only for those who understand the universe is far more violent than it appears from the surface of Earth. And now, with the worst radiation storm slowly fading, humanity prepares for the next phase, a future where Earth must rebuild, while knowing the universe will never be quiet again. As Earth slowly adapts to the long shadow left by the supernova, a deeper transformation begins to unfold, not just in the planet's environment, but in the very direction of human civilization. What started as a survival crisis evolves into a turning point in humanity's relationship with space, technology, and long-term planetary resilience. With radiation levels stabilizing at their new baseline, governments and scientific institutions shift their focus from emergency response to permanent planetary defense. The realization is clear. Earth is vulnerable not only to supernovae, but to a wide range of cosmic threats, solar flares, asteroid impacts, gamma-ray bursts, and interstellar radiation storms. The supernova becomes proof that planetary-scale disasters are not theoretical. They are inevitable. Massive investment flows into space monitoring infrastructure. New generations of telescopes are launched into hardened orbits equipped with radiation-resistant electronics. These observatories continuously scan nearby star systems for unstable massive stars, monitoring any object that could become the next cosmic threat. Early warning systems are established, capable of detecting stellar collapse signatures within seconds. At the same time, planetary shield concepts move from science fiction into engineering reality. Experimental magnetic field generators are deployed in orbit to supplement Earth's natural magnetosphere. These artificial magnetospheres are designed to redirect incoming charged particles, creating localized protection zones above major population centers. Although global coverage remains technologically impossible at first, these systems demonstrate success in reducing radiation exposure during extreme space weather events. Over decades, they are expanded and refined, forming a partial protective grid around the planet. Underground infrastructure continues growing. Entire metropolitan regions now operate beneath Earth's surface. These cities are not temporary shelters. They become permanent living environments, complete with transportation networks, artificial skies, climate-controlled parks, and self-sustaining ecosystems. Life underground evolves into a new cultural norm rather than an emergency adaptation. Psychologically, humanity begins shifting its perception of safety. The surface world is no longer seen as fully secure. Instead, it becomes one layer of habitation among many. People learn to move fluidly between surface cities, underground districts, and orbital habitats. Space stations regain importance as technological hubs. With improved radiation shielding and advanced materials, orbital platforms are redesigned for long-term occupation. These stations serve as research centers, manufacturing hubs, and monitoring outposts that keep constant watch on cosmic conditions. Mars exploration resumes cautiously. Instead of traditional surface colonies, scientists focus on underground habitats protected by thick layers of rock. Lava tubes become ideal shelter zones. These structures provide natural radiation shielding and temperature stability, allowing humanity to establish a limited but sustainable presence on another world. The Moon, despite the radiation environment, regains strategic importance. Lunar bases expand beneath the surface, providing valuable access to helium-3 resources, rare minerals, and deep space launch platforms. The Moon becomes a stepping stone rather than a destination. Meanwhile, Earth's ecosystem continue evolving. Some species adapt faster than others. Forest compositions shift toward radiation-tolerant trees. Grasslands change plant dominance. Animal populations adjust migration routes to safer environments. Over centuries, Earth's biosphere becomes different from anything that existed before the supernova. Human involvement in ecosystem management increases. Conservation is no longer passive, it becomes active engineering. Artificial reefs replace damaged coral systems. Genetic restoration programs revive vulnerable species. Climate regulation technologies stabilize temperature extremes. The boundary between natural and artificial blurs. Earth becomes a partially engineered planet. not because humanity seeks control, but because survival requires intervention. Cultural expression reflects this shift. Art, literature, and film focus heavily on cosmic themes. Humanity's place in the universe becomes a dominant narrative. The supernova enters global mythology as the event that forced civilization to grow up, to stop seeing Earth as isolated and start viewing it as part of a dangerous cosmic environment. Education systems adapt accordingly. Astronomy and planetary science become core subjects taught from early childhood. Students learn about stellar evolution, radiation physics, and planetary defense alongside mathematics and language. Understanding space becomes as important as understanding the ground beneath one's feet. Religious and philosophical movements also change. Some view the supernova as a reminder of cosmic insignificance. Others interpret it as proof of humanity's resilience. New belief systems emerge centered on planetary stewardship and interstellar responsibility. Economically, the global market reorganizes. Industries focused on radiation protection, climate control, underground construction, and space infrastructure dominate. Traditional surface-based industries decline or adapt. Employment shifts toward engineering, environmental management, and space sciences. Political structures evolve toward long-term governance models. Short election cycles become less dominant. Multi-decade planning institutions gain authority. Policies are evaluated not just on immediate outcomes, but on century-scale stability. As centuries pass, the solar system continues stabilizing. The supernova remnant disperses further into interstellar space. Radiation intensity slowly decreases. The heliosphere gradually strengthens, restoring some of its former protective capacity. This slow recovery opens new opportunities. Deep space exploration resumes more aggressively. Humanity begins constructing long-range interstellar probes designed to study nearby star systems. These probes carry advanced shielding and autonomous systems capable of surviving hostile radiation environments. Some scientists propose humanity's boldest idea yet: the creation of artificial interstellar habitats capable of traveling between star systems. Generation ships and autonomous colony vessels are designed as insurance policies against future planetary disasters. The logic is simple. If Earth can be affected by a distant star explosion, then relying on a single planet is dangerous. Spreading civilization across multiple star systems becomes the ultimate survival strategy. As this vision gains momentum, humanity begins its slow transformation into a spacefaring civilization not driven by curiosity alone, but by necessity. The supernova becomes the catalyst for this transition. What once seemed like a rare cosmic event now defines humanity's future direction. Earth remains central, but it's no longer the only cradle of civilization. Over millennia, humanity establishes permanent settlements beyond the solar system. These colonies are designed with lessons learned from Earth's crisis. Radiation shielding, ecological balance, and long-term sustainability are built into their foundations from the beginning. Back on Earth, life continues stabilizing. The planet gradually becomes more resilient. Technology compensates for environmental instability. Ecosystems find new equilibrium points. Earth does not return to its original pre-supernova state. Instead, it evolves into something new, a world shaped by cosmic disaster and intelligent adaptation, a planet where survival is not guaranteed by nature, but maintained by responsibility. And as humanity looks back at the moment a distant star exploded and changed everything, one truth becomes clear. The supernova did not just threaten Earth, it forced humanity to become a planetary civilization, a species that understands its place in the universe, a civilization that no longer looks at the stars only with wonder, but with preparation. Because now humanity knows the universe is not peaceful, it is active, violent, unpredictable, and survival depends on learning how to live within it. As humanity continues adjusting to the transformed cosmic environment, a deeper realization emerges. The supernova did not only alter Earth's atmosphere or radiation levels, it permanently changed how civilization understands time, risk, and survival. The era of assuming stability is over. What replaces it is a new philosophy of planetary resilience. With radiation slowly declining but never fully disappearing, scientists begin redesigning Earth's long-term environmental systems. Instead of reacting to crises, they focus on predictive stabilization. Massive planetary monitoring networks spread across land, sea, and orbit. These systems track atmospheric composition, magnetic field strength, ocean circulation, and solar activity in real time. Artificial intelligence models simulate decades into the future, allowing governments to anticipate threats before they become disasters. Earth's magnetosphere becomes a central focus. Researchers experiment with ways to reinforce the planet's natural magnetic field using orbital superconducting rings. These structures generate controlled magnetic currents that strengthen weak regions of Earth's protective shield. Although expensive and technically complex, early prototypes demonstrate success in reducing radiation penetration during extreme space weather events. At the same time, atmospheric restoration projects scale up. Chemical interventions are used to accelerate ozone regeneration. High-altitude platforms deploy reflective aerosols in controlled quantities to stabilize ultraviolet exposure without disrupting climate balance. These operations are carefully monitored to avoid unintended side effects. The planet slowly becomes a managed system rather than a passive environment. In the biosphere, new evolutionary pressures continue shaping life. Some species adapt genetically over generations, others require human intervention to survive. Conservation programs evolve into active ecosystem engineering. Scientists introduce radiation-resistant plant strains into damaged forests. Marine biologists seed artificial plankton populations to stabilize oxygen production and food chains. These actions raise ethical debates. Humanity is no longer simply protecting nature, it is actively redesigning parts of it. Philosophers question how far intervention should go. Is preserving original ecosystems more important than ensuring planetary survival? Or does survival justify controlled ecological modification? Public opinion gradually shifts toward acceptance. The supernova has demonstrated that passive preservation is no longer enough. Earth must be maintained intentionally. Urban culture reflects this change. Cities integrate green infrastructure directly into architecture. Vertical forests grow along buildings. Artificial wetlands process waste and regulate microclimates. Urban planning prioritizes resilience rather than aesthetics. Transportation systems evolve as well. Underground high-speed transit networks connect major population centers, reducing surface exposure and increasing efficiency. Electric and hydrogen-powered vehicles dominate. Air travel remains limited due to radiation risks at high altitude, shifting long-distance transportation toward high-speed ground networks and orbital transit hubs. Meanwhile, space technology continues advancing. Radiation-hardened spacecraft become standard. New propulsion systems reduce travel time between planets, minimizing exposure. Autonomous repair drones maintain orbital infrastructure continuously, extending satellite lifespans. Deep space observatories expand humanity's awareness of the surrounding galaxy. Astronomers map nearby supernova remnants, unstable stars, and high-energy cosmic regions. The goal is early detection, identifying threats thousands of years before they reach Earth. Humanity also begins exploring the possibility of moving beyond dependence on natural planetary environments entirely. Artificial habitats capable of sustaining closed ecosystems are constructed in orbit. These rotating space stations generate artificial gravity and house tens of thousands of residents. Life inside these habitats becomes increasingly normal. Families grow up in artificial environments with controlled climates and simulated natural cycles. For many, Earth becomes a destination rather than a permanent home. This diversification of living environments marks a critical shift. Humanity is no longer bound to a single planetary surface. Civilization becomes distributed across multiple layers: underground Earth cities, surface megacities, orbital habitats, lunar bases, and Martian underground settlements. With this expansion comes cultural diversification. New social norms develop in space communities. Different gravity levels influence human physiology. Long-term exposure to low-gravity environments produces physical adaptations that separate spaceborne populations from Earth-born humans. Medical science evolves to manage these changes. Genetic therapies correct bone density loss and radiation damage. Artificial organs and cybernetic enhancements become more common, blurring the line between biological and technological life. As centuries pass, the supernova fades into historical memory, but its consequences remain embedded in civilization's structure. Humanity becomes a species shaped by cosmic survival rather than planetary comfort. Education systems emphasize cosmic awareness. Children learn not only Earth's history, but the dynamics of stellar evolution, galactic radiation, and planetary defense strategies. Understanding space becomes essential for citizenship in this new era. Political institutions also transform. Planetary governance frameworks replace traditional nation-based systems for managing global resources and environmental stability. Local governments still exist, but planetary coordination becomes essential for survival. Conflicts do not disappear. Competition over resources, technology, and space territories continues. However, the shared memory of near catastrophe encourages cooperation during major crises. Humanity learns that internal conflict weakens planetary defense. Meanwhile, scientists begin observing subtle but important long-term trends. Earth's climate, while stabilized artificially, slowly adapts to the new radiation environment. Certain atmospheric patterns become permanent. Ocean currents adjust to altered temperature gradients. New climate zones emerge. These changes reshape agriculture again. Crop zones migrate toward new latitudes. Genetic crop diversity expands dramatically as scientists develop varieties suited to different environmental niches. Human diets evolve accordingly. New food sources emerge, including lab-grown proteins, algae-based nutrition, and genetically optimized plants. Traditional agriculture becomes only one part of a diversified food ecosystem. Cultural identity evolves with these shifts. The idea of natural Earth becomes more symbolic than literal. Earth is now a hybrid world, part natural ecosystem, part engineered environment. Artists, writers, and philosophers reflect on this transformation. Some mourn the loss of untouched wilderness. Others celebrate humanity's ability to adapt and preserve life under extreme conditions. As time continues forward, humanity begins preparing for the next great challenge: interstellar vulnerability. The supernova demonstrated that even distant stars can threaten planetary systems. This realization pushes scientists to study galactic dynamics more deeply. They map regions of high stellar density, supernova clusters, and cosmic radiation corridors. Future settlement planning takes these maps into account. New colonies are placed in regions of space with lower long-term radiation risk. Humanity begins treating the galaxy as an environment with dangerous zones and safer regions, similar to how ancient humans once mapped floodplains and volcanic regions on Earth. With this knowledge, civilization becomes proactive rather than reactive. The supernova that once threatened extinction now becomes the foundation of humanity's survival strategy. It taught humanity to think beyond years and decades, to plan for centuries, to design civilizations that can survive not just planetary disasters, but galactic ones. And as humanity continues expanding outward, carrying Earth's history across the stars, one lesson remains at the core of civilization. The universe is not built for life. Life survives because it adapts, because it learns, because it prepares, and because it refuses to disappear quietly, even when the cosmos itself turns hostile. As humanity settles into this new era of cosmic awareness, a deeper transformation begins to unfold, one that reshapes not only technology and infrastructure, but the very identity of civilization itself. The supernova is no longer remembered merely as a disaster. It becomes a defining moment in human history, similar to the discovery of fire or the Industrial Revolution. It marks the transition from a species bound to one planet into a civilization that must survive on cosmic timescales. With planetary defense systems now operating continuously, Earth becomes the most monitored world humanity has ever inhabited. Thousands of orbital platforms circle the planet, scanning radiation levels, tracking solar activity, and observing interstellar particle flows. Data streams pour into global control centers, where artificial intelligence systems coordinate responses in real time. The planet itself feels alive with sensors and feedback loops, constantly adjusting to maintain stability. This level of monitoring produces a strange psychological effect. Humanity becomes hyper-aware of invisible cosmic forces. People grow accustomed to hearing daily reports about solar wind pressure, radiation flux, and magnetic field fluctuations. Space weather forecasts become as common as traditional weather updates once were. The sky is no longer simply something to admire, it is something to manage. At the same time, scientific understanding of stellar death advances rapidly. Supernova research becomes one of the most funded fields in astrophysics. Scientists simulate stellar collapse in unprecedented detail, studying how different types of supernovae affect surrounding planetary systems. They learn to identify early warning signs in distant stars, subtle changes in neutrino emissions, gravitational oscillations, and energy output that signal imminent collapse. This knowledge allows humanity to detect potential supernova threats thousands of years in advance. While this does not allow evacuation of entire planets, it provides time to prepare shielding systems, relocate vulnerable populations, and adjust orbital infrastructure. Preparation becomes humanity's greatest weapon. Meanwhile, Earth's role within civilization continues evolving. As more people live in orbital habitats and off-world settlements, Earth transitions from being the centre of population to being the symbolic heart of humanity. It becomes a protected heritage world, not abandoned but preserved. Large regions of the planet are designated as planetary reserves. These areas are shielded from industrial development and maintained for ecological restoration. Scientists use advanced techniques to revive damaged ecosystems, reintroducing extinct species through genetic reconstruction, and restoring forests and coral reefs where possible. Earth slowly becomes a living museum of biological history, showcasing the evolution of life under changing cosmic conditions. Cultural traditions reflect this shift. Annual global observances commemorate the supernova event, not as a tragedy, but as a reminder of vulnerability and resilience. Educational ceremonies teach young generations about the moment humanity realized it was not protected by the universe. Religious and philosophical thought evolves further. Many belief systems incorporate cosmic responsibility into their teachings. The idea that intelligent life carries the duty to protect itself and its environment becomes widespread. At the same time, spaceborne generations begin developing distinct identities. Children born in orbital habitats grow up under artificial gravity and controlled skies. Their perception of Earth is shaped by virtual reality experiences and historical records rather than direct memory. These space communities develop unique cultures, languages, and social structures. Some view Earth as sacred. Others see it as one of many worlds in humanity's growing network of habitats. This diversity strengthens civilization, but also introduces new challenges. Differences in environment, gravity, and resource access create political tension. New laws and governance models are needed to manage interplanetary relationships. To address this, humanity establishes a multiplanetary council responsible for coordinating policy across Earth, lunar settlements, orbital habitats, and Martian colonies. This council does not replace local governments, but provides unified decision-making during planetary-scale emergencies. One of its primary missions is maintaining cosmic defense readiness. Regular drills simulate supernova radiation events, solar superstorms, and asteroid impact scenarios. Humanity treats disaster preparedness as a permanent responsibility rather than a temporary response. Technological innovation accelerates under this constant pressure. Materials science produces ultra-dense radiation shields. Quantum communication networks allow instant coordination across vast distances. Autonomous construction robots build habitats in extreme environments where humans cannot safely work. Medical science continues advancing as well. New therapies repair radiation-damaged DNA. Artificial organs become commonplace. Life expectancy increases as healthcare adapts to harsh environmental conditions. As a result, humanity becomes physically and biologically different from its ancestors. space-adapted populations develop stronger bones, modified muscle structures, and enhanced radiation resistance through genetic therapies. The human species slowly diversifies into multiple variations optimized for different environments. This raises profound ethical questions. What does it mean to remain human when biology becomes adjustable? Is adaptation survival or transformation into something new? Society debates these issues intensely. Some communities embrace biological modification as necessary evolution. Others resist, preserving traditional human biology and choosing to remain Earth-based. Despite disagreements, civilization continues moving forward. Meanwhile, astronomers observe something remarkable. The supernova remnant that once threatened Earth begins forming new structures in interstellar space. Shockwaves compress nearby gas clouds, triggering the birth of new stars. Regions once filled with destructive energy now become stellar nurseries. This discovery reframes the supernova's role in cosmic history. What was once seen only as a threat is now understood as part of the universe's cycle of creation and destruction. The same explosion that endangered Earth is also responsible for forming the heavy elements that make planets, technology, and life itself possible. This realization influences humanity's worldview. The universe is no longer seen as purely hostile. It is chaotic, violent, but also creative. Life exists not despite this chaos, but because of it. Earth's survival becomes part of this larger cosmic story. As millennia pass, the immediate danger of the supernova fades into deep history. Radiation levels gradually return closer to normal. The heliosphere strengthens. Planetary stability improves. Yet humanity does not forget. The infrastructure built during the crisis remains active. Planetary defense systems stay operational. Space monitoring continues. Preparedness becomes embedded in civilization's DNA. Humanity does not return to complacency. Instead, it embraces its new role as a cosmic civilization, one that understands the universe is unpredictable, and survival depends on awareness, adaptation, and cooperation. Looking back, historians describe this period as the moment humanity stopped thinking like a species confined to Earth and started thinking like a species belonging to the galaxy. The supernova that once threatened extinction becomes the catalyst for expansion, resilience, and long-term survival. And as humanity continues spreading among the stars, carrying Earth's legacy across interstellar distances, one lesson remains permanent. The universe will never protect life. Life must protect itself. And those who learn this truth early are the ones who endure. As humanity moves deeper into this cosmic era, the long-term consequences of the supernova reshape civilization in ways no one originally predicted. What began as planetary defense slowly evolves into something far larger. A transformation of how humanity organizes itself across space and time. With Earth stabilized and planetary monitoring systems fully operational, attention shifts outward. Scientists realize that if a supernova can affect the solar system from dozens of light years away, then other regions of the galaxy may be far more dangerous than previously assumed. This leads to the creation of the Galactic Risk Mapping Program, a massive scientific effort to chart high-risk stellar zones across nearby space. Using advanced telescopes and gravitational wave detectors, astronomers identify clusters of massive stars nearing the end of their life cycles. These regions become classified as cosmic hazard zones. Humanity begins planning future settlements based not only on resource availability, but also on long-term stellar stability. Star systems with low supernova probability become priority targets for colonization. This marks a turning point. Humanity no longer explores space randomly, it explores strategically. Colonization missions are redesigned with survival in mind. New generation ships and autonomous colony vessels are built with thick radiation shielding, self-repair systems, and closed-loop ecosystems capable of sustaining life for centuries without external support. These vessels are not temporary transports, they are mobile worlds. Some of these ships travel slowly toward nearby star systems, carrying thousands of settlers in cryogenic or long-duration habitats. Others remain within the solar system, serving as test platforms for long-term isolation and sustainability experiments. Earth, meanwhile, becomes a command center for this expanding civilization. Orbital control stations coordinate interplanetary traffic. Communication relays stretch across vast distances, linking Earth with Mars, lunar bases, and outer system habitats. Humanity becomes increasingly interconnected, despite spreading farther apart. Cultural identity adapts again. People begin identifying not just by nationality or planet, but by generation group. Earth-born, Mars-born, station-born, and ship-born populations develop unique experiences and perspectives. Ship-born communities in particular develop distinct cultures. Raised inside artificial worlds travelling through deep space, these populations grow up without direct experience of planetary skies or natural gravity. Their understanding of home becomes abstract, defined by community rather than geography. This diversity challenges traditional ideas of society. Education systems evolve to accommodate different environmental backgrounds. Political representation expands to include mobile populations and off-world habitats. Citizenship becomes tied to civilization rather than territory. As humanity spreads, the concept of planetary defense expands into interstellar defense. Instead of only protecting Earth, civilization begins designing protective infrastructure for entire star systems. Magnetic shields, radiation deflectors, and early warning networks are planned around future colonies. These efforts require unprecedented cooperation. No single nation or group can manage interstellar-scale projects alone. Humanity gradually transitions into a more unified planetary civilization, not without conflict, but driven by shared survival goals. Back on Earth, life becomes more stable, but never returns to its old simplicity. Cities remain partially underground. Climate regulation continues operating. Artificial ecosystems coexist with natural ones. The planet exists in a permanent state of managed balance. Children born in this era grow up learning about the supernova as ancient history. They study it in school the way earlier generations studied ice ages or mass extinctions. Yet its influence is everywhere, in infrastructure design, space policy, and cultural values. Art and storytelling reflect humanity's expanded horizon. Stories no longer focus only on Earth-based struggles. They explore life aboard starships, civilizations on distant worlds, and the psychological challenges of living far from the sun. Music incorporates cosmic themes. Visual art blends natural planetary imagery with abstract representations of radiation, gravity, and space-time. humanity's creative expression becomes as expansive as its physical presence. Religion and philosophy continue adapting. Some belief systems embrace the idea that humanity has become a guardian of life in the galaxy. Others emphasize humility, reminding people that even advanced civilizations remain vulnerable to forces beyond their control. As centuries pass, scientific understanding of supernova effects becomes incredibly detailed. Researchers study ancient extinction events on Earth and correlate them with possible nearby stellar explosions. Evidence emerges that supernovae may have influenced life's evolution multiple times in the planet's past. This realization reframes Earth's biological history. Humanity begins to see itself not as separate from cosmic events, but as shaped by them. Life itself is influenced by stellar death. The same explosions that threatened extinction also created the heavy elements necessary for complex biology and technology. Iron in blood, calcium in bones, silicon in computers, all forged in ancient stars. The supernova that endangered Earth is part of the same cosmic cycle that made humanity possible. This perspective brings a strange sense of balance. Destruction and creation are intertwined. As the supernova remnant that once affected the solar system continues dispersing across space, its influence becomes part of the interstellar environment. New star systems form from compressed gas clouds. Planets begin forming around these newborn stars, seeded with elements created by stellar explosions. Humanity observes these processes closely, learning how cosmic events shape the galaxy over millions of years. This knowledge informs future settlement planning and long-term survival strategies. Meanwhile, Earth's ecosystems slowly stabilize into new equilibrium states. Some species recover, others disappear. New species emerge through adaptation and genetic intervention. Biodiversity evolves in ways never seen before. Human society becomes increasingly resilient. Infrastructure is built with redundancy. Energy systems diversify. Food production spreads across multiple environments. No single disaster can now threaten civilization entirely. The concept of planetary fragility becomes deeply ingrained in culture. People no longer assume permanence. Instead, they value adaptability, sustainability, and long-term thinking. This mindset changes politics. Leaders are judged by their ability to prepare for future generations rather than short-term economic growth. Large-scale projects focus on environmental stability, education, and scientific advancement. As humanity continues expanding outward, Earth remains central emotionally, but not physically. It becomes a symbol of origin, resilience, and survival. Pilgrimages to preserved natural regions become common. People travel to experience forests, oceans, and mountains maintained as heritage environments. Earth is no longer just a home. It is a living archive of humanity's beginnings. And as starships leave the solar system carrying new generations into unknown space, they carry more than technology. They carry lessons learned from the moment a distant star exploded and forced humanity to change. They carry the understanding that survival is not guaranteed by comfort. It is earned through preparation, through cooperation, through respect for cosmic forces. The supernova that once threatened extinction becomes part of humanity's identity. A reminder that the universe is powerful, that life is fragile, and that intelligence, when used wisely, can transform disaster into evolution. As humanity continues its journey across the galaxy, it does so with eyes open, aware of danger, aware of beauty, and prepared to face whatever the cosmos sends next. As humanity's expansion accelerates beyond the boundaries of the solar system, the legacy of the supernova continues shaping decisions on a galactic scale. What was once a singular disaster becomes the foundation for a new survival doctrine. Civilization must never depend on a single star, a single planet, or a single region of space. Interstellar colonies begin forming networks rather than isolated settlements. Instead of building lone outposts, humanity establishes clusters of habitats around stable stars, each connected through high-capacity communication relays and autonomous supply routes. These clusters are designed to support one another in times of crisis. If one system suffers stellar instability, neighbouring systems can absorb refugees and redistribute resources. This network approach changes how humanity thinks about borders. Space is no longer divided by lines on a map, but by zones of influence defined by gravitational systems and resource availability. Political power shifts from centralized planetary governments toward federated star system alliances that coordinate defense, trade, and scientific research. Earth's role in this new structure becomes symbolic and strategic. It remains the cultural capital of humanity, hosting the largest historical archives, educational institutions, and interplanetary coordination centers. Major decisions regarding cosmic defense and exploration still flow through Earth-based councils, even as populations disperse. Technological innovation continues accelerating. One of the most significant developments is the creation of adaptive habitat shells, massive artificial structures capable of reshaping their internal environments in response to external cosmic conditions. These habitats can adjust gravity, radiation shielding, atmospheric composition, and temperature dynamically. They are designed not just for comfort, but for survival under unpredictable galactic conditions. Some of these habitats orbit stable stars, others drift between systems, functioning as mobile civilizations. These wandering habitats allow humanity to relocate entire populations away from danger zones if necessary, creating a form of cosmic migration unprecedented in history. Biological adaptation becomes more deliberate. Genetic medicine advances to the point where humans can be optimized for different environments. Space-adapted populations develop increased radiation resistance, enhanced bone regeneration, and modified metabolic processes suited for low-gravity living. While controversial, these changes become widespread. Humanity slowly evolves into a species with multiple variations, each adapted to specific cosmic environments. Earthborn humans, spaceborne populations, and colony-adapted groups coexist, forming a diverse interstellar civilization. This diversification sparks philosophical debate. Some argue that humanity is losing its original identity. Others believe this is the natural continuation of evolution, not random mutation, but guided adaptation. Education systems adapt accordingly. Students learn about evolutionary engineering alongside biology. Ethics courses explore the implications of modifying life. History classes frame humanity's transformation as part of a long survival arc that began with the supernova crisis. Cultural traditions reflect this new identity. Instead of celebrating only planetary events, humanity begins commemorating cosmic milestones: the founding of the first interstellar colony, the launch of the first-generation ship, the stabilization of Earth's radiation environment, art evolves into new forms designed for multi-world audiences. Holographic performances allow artists to perform simultaneously across star systems. Virtual reality exhibitions recreate ancient Earth environments, allowing people born light years away to experience forests, oceans, and skies that shaped humanity's origins. Religion and spirituality continue transforming. Many belief systems adopt cosmic symbolism, viewing humanity's expansion as part of a universal cycle of creation and renewal. Some faiths interpret the supernova as a test that forced humanity to transcend planetary limitations. Meanwhile, scientific research deepens humanity's understanding of stellar death. Astronomers begin detecting early-stage stellar collapse processes with unprecedented accuracy. Gravitational wave observatories identify subtle vibrations signaling core instability in massive stars. Neutrino detectors provide advance warning of internal nuclear reactions approaching critical thresholds. This capability allows humanity to predict supernova events thousands of years before they occur, while evacuation of entire systems remains impossible, capable of responding automatically to cosmic disturbances. Over time, Earth's environment becomes more stable than it was immediately after the supernova, though it never returns to its original untouched state. Instead, it exists as a hybrid world, part natural ecosystem, part engineered environment. Human population on Earth stabilizes at lower levels compared to off-world settlements. Many people choose to live in orbital habitats or other star systems, leaving Earth less crowded and more focused on research, preservation, and education. This shift allows large regions of Earth to recover naturally. Forests expand. Wildlife populations rebound in protected zones. Some ecosystems return to near pre-supernova conditions, while others evolve into entirely new forms. The oceans, though permanently altered, regain productivity through artificial plankton seeding and controlled nutrient cycling. Fisheries stabilize. Marine biodiversity adapts to new environmental parameters. Humanity begins documenting these long-term ecological changes in detail, creating the largest planetary database ever assembled. This data becomes invaluable for managing future colonies and terraforming projects. As centuries pass, the memory of the supernova transforms again. It is no longer remembered primarily as a threat. It becomes the origin point of humanity's cosmic expansion. A moment when civilization was forced to confront the reality that survival on one planet is never guaranteed. Young generations grow up viewing the universe differently. They do not see space as distant or unreachable. They see it as part of daily life. Travel between planets becomes routine. Communication across star systems becomes normalized. This new generation carries fewer emotional ties to Earth, but strong respect for its role in history. Earth becomes a place people visit to learn about humanity's beginnings, rather than a place everyone expects to live. As humanity spreads farther into the galaxy, it encounters new challenges, unfamiliar planetary environments, exotic radiation fields, and unknown astrophysical phenomena. Yet the lessons learned from surviving a nearby supernova provide a foundation for facing these new dangers. The mindset of preparation, adaptation, and long-term thinking becomes deeply embedded in civilization. Humanity no longer measures success only in economic growth or territorial expansion. It measures success in resilience, in the ability to survive cosmic threats, in the ability to adapt to extreme environments, in the ability to preserve life across vast distances and timescales. And as humanity continues pushing outward, carrying Earth's history and the memory of a star's violent death, one truth remains at the core of civilization. The universe is not a safe place, but it is a place where life can endure if it learns how to move, how to adapt, and how to prepare for the next explosion that will one day light up another sky. As humanity's interstellar network grows stronger, civilization enters a phase where survival is no longer reactive, but anticipatory. The memory of the supernova becomes embedded in long-term planning models, shaping how societies design infrastructure, allocate resources, and define progress itself. One of the most important changes is the shift from planetary scale thinking to system scale thinking. Instead of focusing only on protecting individual worlds, humanity begins managing entire star systems as integrated environments. Energy production, habitat placement, asteroid mining, and radiation shielding are coordinated across planetary orbits to maximize stability and resilience. Asteroid belts become strategic assets. Mining operations extract rare metals while simultaneously reshaping asteroid trajectories to create artificial radiation shields. Some large asteroids are repositioned into stable orbits, forming protective rings that absorb high-energy particles before they reach inhabited zones. These structures also serve as emergency shelters and storage facilities. Orbital engineering becomes a dominant field. Engineers design massive structures capable of manipulating solar radiation, redirecting stellar winds, and stabilizing planetary climates. Sunshade arrays are deployed around vulnerable planets to reduce radiation exposure and regulate surface temperatures. Magnetic field generators orbit key habitats, creating artificial magnetospheres where natural ones are weak or non-existent. These technologies allow humanity to colonize environments once considered uninhabitable. Worlds with thin atmospheres, extreme temperatures, or high radiation levels become viable through artificial environmental control. Civilization expands not only in safe regions, but into challenging ones that would have been impossible to inhabit before the supernova era. At the same time, scientific understanding of cosmic radiation deepens dramatically. Researchers identify patterns in galactic radiation cycles, mapping high-risk periods when cosmic ray intensity naturally increases due to interstellar magnetic field shifts. This allows colonies to adjust activity schedules, activate additional shielding, and temporarily relocate vulnerable populations during peak exposure events. Medical science evolves alongside these discoveries. Radiation medicine becomes a specialized discipline. New treatments repair cellular damage at the molecular level. Nanotechnology allows targeted DNA repair inside living cells. Artificial organs capable of withstanding extreme environments replace damaged biological systems. Life expectancy increases again, even in harsh cosmic conditions. Humanity learns not just to survive radiation, but to mitigate its effects effectively. Social structures continue adapting. Traditional concepts of work, education, and community change in space-based societies. Automation handles most physical labor, while humans focus on research, creativity, and system management. virtual collaboration becomes central, allowing people across star systems to work together in shared digital environments. Education becomes lifelong and adaptive. Citizens continuously update skills as technology evolves. Spaceborne generations receive training tailored to their environments, learning orbital mechanics, radiation safety, and habitat maintenance as basic survival knowledge. Culture reflects this technological integration. Art installations float in zero gravity. Music is composed to resonate through artificial atmospheres. Architecture adapts to environments where gravity and weather can be controlled. Humanity's creative expression expands beyond traditional planetary limitations. Meanwhile, Earth's role continues shifting toward preservation and research. Large regions of the planet are designated as long-term ecological sanctuaries. These areas are protected from industrial development and carefully monitored to observe how ecosystems adapt to post-supernova conditions over centuries. Earth becomes a living laboratory. Scientists study natural recovery processes alongside engineered restoration efforts. This research informs planetary management strategies for other worlds, helping colonies maintain ecological balance. Tourism evolves as well. People travel to Earth to experience preserved rainforests, oceans, and historical cities maintained as heritage zones. These journeys become educational pilgrimages, connecting interstellar populations with humanity's origins. Politically, humanity experiments with new governance models designed for multi-world civilization. Decision-making structures incorporate artificial intelligence advisors that analyze long-term outcomes across centuries. Policies are evaluated not just for immediate benefits, but for their impact on planetary stability and interstellar resilience. Conflicts still arise, but large-scale wars become less common. The interconnected nature of civilization makes cooperation more beneficial than competition. Shared infrastructure, energy grids, and defense systems encourage diplomatic solutions over military confrontation. Security, however, remains important. Planetary defense fleets patrol high-risk regions of space, monitoring asteroid threats, radiation storms, and unstable stellar activity. These fleets are not weapons of conquest, but tools of protection designed to safeguard civilian populations. As humanity's technological capabilities expand, scientists begin exploring even more ambitious ideas. One such concept is stellar engineering, the possibility of influencing star behavior to reduce supernova risk. While direct control of stars remains far beyond current capabilities, researchers study ways to extract energy from unstable stars or manipulate surrounding matter to delay collapse. Another emerging field is galactic migration planning. Humanity begins considering long-term movement across the galaxy to avoid regions with high supernova frequency. This strategy treats civilization as a mobile presence rather than a static one, capable of shifting its center of population over millions of years. These ideas may seem extreme, but they reflect a new understanding of survival. Civilization is no longer tied to specific locations. It becomes adaptable, mobile, and distributed. Philosophically, this transformation forces humanity to reconsider its relationship with permanence. Ancient civilizations built monuments hoping to last forever. Modern humanity learns that nothing in the universe is permanent, not stars, not planets, not even galaxies. Instead of permanence, the new goal becomes continuity, ensuring that life, knowledge, and culture persist even as physical environments change. Libraries are no longer just buildings. They become distributed digital archives stored across multiple star systems. Human history is preserved redundantly to prevent loss from any single disaster. Languages evolve and branch, but translation systems maintain communication across civilizations. Cultural heritage becomes something actively maintained rather than passively inherited. As centuries pass, humanity's relationship with the cosmos becomes more balanced. Fear of cosmic disasters does not disappear, but it's replaced by preparedness and understanding. The supernova that once caused panic now serves as a reference point for resilience. Young generations grow up without the emotional trauma of the event, but with full awareness of its importance. They see it as the moment humanity matured into a cosmic species. Education programs include simulations of historical disasters, teaching students how to respond to radiation storms, system failures, and planetary emergencies. Preparedness becomes cultural instinct rather than institutional policy. As civilization stabilizes across multiple star systems, Earth's environment continues slowly healing. Radiation levels decline further, ecosystems adapt more fully. Some regions regain near natural balance, while others remain managed environments. Earth becomes quieter, less crowded, more reflective. It serves as a reminder of humanity's origins and the fragility of planetary life. Looking outward, humanity now stands at the threshold of becoming a truly galactic civilization. The infrastructure built in response to one nearby supernova has created the foundation for expansion across thousands of star systems. What began as a catastrophe becomes the catalyst for humanity's greatest transformation. The supernova forced civilization to confront cosmic reality. It taught humanity that survival requires foresight, that comfort is temporary, that stability must be built, not assumed. And as humanity continues moving forward, spreading across space, carrying Earth's memory and lessons with it, the legacy of that distant, exploding star remains alive, not as fear, but as wisdom, a reminder that the universe is powerful, that life is fragile, and that intelligence, when guided by cooperation and preparation, can turn even cosmic disaster into the beginning of something far greater. As humanity's expansion stabilizes across multiple star systems, civilization enters what historians later call the era of cosmic maturity. This is not defined by rapid technological breakthroughs or explosive growth, but by balance, a careful equilibrium between exploration, preservation, and long-term survival planning shaped by the memory of the supernova that once threatened Earth. At this stage, humanity no longer measures success by how far it can expand, but by how well it can sustain what it has already built. Colonies across star systems begin shifting their focus from rapid construction to ecological and cultural stability. Artificial habitats evolve into self-regulating environments capable of maintaining balanced ecosystems without constant human intervention. These habitats become miniature worlds, complete with forests, lakes, agricultural zones, and wildlife corridors designed to mimic natural planetary cycles. Earth plays a central role in this transition. As populations migrate outward, Earth becomes increasingly protected. large-scale industrial activity is phased out. The planet is preserved as a biological archive and cultural sanctuary. Scientists maintain long-term ecological experiments, observing how ecosystems adapt over centuries to post-supernova conditions. New planetary preservation laws ensure Earth's landscapes remain largely untouched. Forest reserves expand. Ocean conservation zones cover vast portions of the seas. Wildlife corridors connect ecosystems across continents. Humanity becomes not just a resident of Earth, but its caretaker. This stewardship mindset spreads beyond Earth. Colonies on Mars and other worlds adopt similar preservation models. Instead of fully terraforming planets into Earth-like replicas, settlers learn to adapt their habitats to existing planetary conditions. The goal becomes coexistence rather than domination. Technological systems evolve to support this philosophy. Environmental monitoring networks track biodiversity, atmospheric stability, and energy flows in real time. Artificial intelligence optimizes resource usage to minimize waste and ecological disruption. Energy grids rely heavily on fusion and stellar harvesting technologies, reducing environmental strain. Social structures also mature. Interstellar societies move away from extreme inequality. Universal access to education, healthcare, and basic resources become standard across human space. The understanding that planetary instability affects everyone encourages cooperation over competition. Cultural identity becomes increasingly layered. People identify with their local habitats, star systems, and humanity as a whole simultaneously. Festivals celebrate not only planetary events, but cosmic milestones such as the founding of new colonies and the anniversaries of major astronomical discoveries. Education systems emphasize planetary literacy. Children learn not just mathematics and language, but how ecosystems function, how radiation affects biology, and how stellar evolution influences planetary safety. This knowledge becomes essential for responsible citizenship in a cosmic civilization. Art and philosophy flourish during this period. With survival no longer dominating daily life, humanity turns inward to explore meaning and identity. Artists create works inspired by the vastness of space, the fragility of life, and the beauty of adaptation. Writers tell stories that span generations and star systems, reflecting the long-time horizons of interstellar existence. Religious and spiritual traditions evolve again. Many belief systems emphasize interconnectedness between life and the universe. The supernova becomes a symbolic reminder of impermanence and renewal. Instead of fearing cosmic forces, people learn to respect them. Meanwhile, scientific research continues pushing boundaries. Astronomers refine predictive models of stellar behavior, allowing civilization to forecast potential supernova threats tens of thousands of years in advance. Gravitational wave observatories detect subtle changes in distant stars, providing unprecedented insight into stellar life cycles. This knowledge allows humanity to plan far ahead. Colonies near unstable regions are gradually relocated. Infrastructure is reinforced. Entire populations migrate smoothly rather than reacting to emergencies. Medical science reaches new heights. Radiation-resistant therapies become standard. Genetic treatments repair cellular damage and prevent long-term health effects. Life expectancy increases further, allowing individuals to witness multiple generations of planetary and cultural change. As humanity lives longer, historical memory deepens. People remember the supernova not as distant legend, but as part of collective identity passed down through education and cultural tradition. Museums across star systems preserve interactive records of Earth's transformation, allowing visitors to experience simulated versions of the radiation storm, heliosphere collapse, and planetary adaptation. These experiences reinforce humility. They remind people that civilization exists only because previous generations prepared and adapted. Economically, humanity shifts towards sustainability-based growth models. Instead of endless expansion, economies focus on maintaining stable resource cycles. Recycling, energy efficiency, and long-term planning become core principles. Resource extraction is carefully regulated to avoid destabilizing planetary environments. Trade networks connect star systems through automated cargo fleets. These fleets transport raw materials, manufactured goods, and biological resources using optimized routes designed to minimize radiation exposure and energy consumption. Politically, governance becomes more collaborative. Planetary councils coordinate with interstellar assemblies to manage shared challenges. Artificial intelligence advisors simulate outcomes of large-scale decisions, helping leaders choose paths that maximize stability across centuries. Conflicts still exist, but they are increasingly resolved through negotiation and arbitration rather than violence. The memory of planetary vulnerability discourages large-scale war, as destruction would weaken collective survival. As this era progresses, humanity begins facing new philosophical questions. If civilization can survive supernova, radiation storms, and planetary instability, what is the ultimate goal? Expansion, preservation, exploration of consciousness itself? Some communities focus on scientific discovery, pushing deeper into the galaxy to understand dark matter, black holes, and cosmic structure. Others emphasize cultural preservation, ensuring humanity's stories, languages, and traditions endure across generations. Earth remains central to this debate. It stands as a reminder of origins and limitations. Many people travel to Earth not to live permanently, but to reconnect with the planet that shaped humanity's first identity. Walking through preserved forests, observing oceans stabilized by technology, and standing beneath skies once altered by cosmic radiation, visitors gain perspective on how far civilization has come. As millennia pass, the immediate physical effects of the supernova fade almost completely. Radiation levels approach natural galactic background values. The heliosphere strengthens, Earth's environment becomes more stable, yet the psychological and cultural impact never disappears. The supernova becomes humanity's shared origin story of cosmic awareness. It marks the moment civilization realized it was not alone in the universe, not in the sense of extraterrestrial life, but in the sense of being connected to vast cosmic forces beyond control. This awareness reshapes humanity's identity permanently. No longer just inhabitants of Earth, no longer just explorers of space, but caretakers of life in a universe that is both creative and destructive. As humanity continues evolving, expanding, and adapting, the memory of that distant, exploding star remains quietly present in every major decision. A reminder that survival is not guaranteed, that progress is not automatic, that resilience is earned, and that intelligence, when guided by cooperation and long-term vision, can turn even the most violent events in the universe into opportunities for growth. In this era of cosmic maturity, humanity does not see itself as the master of the universe. It sees itself as a participant, a small but persistent form of life learning how to endure in a vast and unpredictable cosmos. And that understanding, born from the shock of a supernova, becomes the foundation of humanity's future among the stars. As humanity reaches the final stage of its transformation, the long journey that began with a distant star's violent death comes full circle. What was once a sudden cosmic threat has reshaped civilization into something far greater than anyone could have imagined. A species no longer confined to one planet, no longer dependent on a single star, and no longer blind to the dangers hidden in the universe. By this era, humanity exists across countless worlds, habitats, and star systems. Earth remains preserved as the birthplace of civilization, a living archive of biological and cultural history. Its forests, oceans, and skies are carefully maintained, not for economic profit, but for memory and meaning. Earth is no longer crowded, no longer industrialized, but deeply respected. It stands as proof that survival is not only about expansion, but about preservation. Interstellar civilization operates as a vast, interconnected network. Communication relays link distant colonies. Energy flows between systems through advanced stellar harvesting and fusion networks. Knowledge is shared instantly across light years. Humanity becomes something closer to a distributed intelligence than a traditional planetary society. Children born in this era grow up with a different understanding of reality. They learn early that stars are not eternal, that planets can be reshaped by cosmic forces, and that survival depends on preparation rather than luck. The supernova is no longer just a historical event. It is a foundational lesson taught in every educational system across human space. In classrooms on distant worlds, students study the moment Earth's sky is filled with radiation, when the heliosphere collapsed inward and humanity faced planetary vulnerability. They analyze how earlier generations responded, not with surrender but with innovation, cooperation, and long-term thinking. These lessons become part of civilization's moral framework. Technological systems now operate almost invisibly. Planetary shields adjust automatically. Habitat environments self-regulate. Artificial intelligence networks monitor cosmic threats continuously, predicting stellar instabilities thousands of years in advance. Humanity no longer reacts to disasters. It anticipates them. This ability fundamentally changes how civilization plans for the future. Instead of fearing cosmic destruction, humanity integrates it into long-term strategy. Migration routes are planned around stellar life cycles. Colonies are positioned based on galactic stability maps. Even cultural centers are distributed to prevent the loss of knowledge in any single event. Biological evolution also continues. Humans adapt further to diverse environments. Some populations evolve stronger radiation resistance. Others adapt to low-gravity habitats or artificial atmospheres. Humanity becomes a multi-environment species, capable of thriving in conditions that would once have been deadly. Yet despite these changes, one thing remains constant: the emotional connection to Earth. Pilgrimages to Earth become common across star systems. People travel vast distances to walk through preserved forests, to see oceans shaped by ancient tides, and to stand beneath skies that once witnessed humanity's first steps into cosmic awareness. Earth becomes a place of reflection, not necessity. Ceremonial events mark the anniversary of the supernova. Across human space, cities dim their lights for a moment of silence. Artificial skies display simulations of the explosion, not as spectacle, but as remembrance. These rituals honor the generation that endured the crisis and built the foundation of cosmic civilization. Philosophically, humanity arrives at a deeper understanding of its place in the universe. The supernova teaches that destruction and creation are inseparable. The same explosions that threaten life also create the elements that make life possible. Civilization learns to exist within this cycle rather than trying to escape it. Rather than seeking immortality for planets or stars, humanity focuses on continuity of life and knowledge. Archives are stored across multiple star systems. Cultural heritage is preserved redundantly. Even if entire regions of space become uninhabitable in the future, civilization will endure elsewhere. This mindset transforms humanity's relationship with time. People no longer think in decades or centuries alone. They think in thousands of years, in stellar life cycles, in galactic movements. Civilization becomes patient, strategic, and resilient. As exploration continues, humanity encounters environments even harsher than those near Earth. Regions saturated with radiation, unstable stars, and exotic cosmic phenomena. Instead of retreating, civilization adapts. New shielding technologies are developed. Habitats evolve. Survival strategies improve. The universe remains dangerous, but humanity is no longer fragile. Looking back across history, scholars describe the supernova as the moment humanity stopped seeing the universe as distant and harmless. It forced civilization to confront reality. Earth was never isolated. The cosmos was always influencing life. What changed was awareness. Awareness led to preparation. Preparation led to adaptation. Adaptation led to expansion. The supernova did not destroy humanity. It awakened it. In the far future, when humanity exists across hundreds of star systems, the story of Earth's near encounter with stellar death remains central. It is told not as a tale of fear, but as a story of growth. A story of how a fragile species learned to survive cosmic violence. A story of how intelligence transformed disaster into evolution. A story of how life refused to remain confined to one world. And as humanity continues moving deeper into the galaxy, carrying Earth's memory across the stars, one truth remains at the heart of civilization. The universe will always be unpredictable. Stars will continue to die. Cosmic explosions will never stop. But life, when guided by knowledge, cooperation, and preparation, can endure even the most violent chapters of cosmic history. What began as a supernova near our solar system did not end Earth's story. It expanded it beyond the boundaries of one planet, beyond one star, and into the vast, dangerous, beautiful universe itself.